have already heard this trick. Actually, I trust numerical computation, but I don't trust computer. So I shall use transparencies like in the old time. And okay, the title of my talk is, it was how to spoil frictional contact algorithm. Then I didn't dare to write it and say how not to spoil. Actually, I should have said, or try not to spoil. And this is the plane of my talk. Now, I would like to highlight some technical about numerical computation, frictional contact algorithm. And as a basis, I shall use the non-smooth contact dynamic, shortly contact dynamics, as mentioned by Jean-Jacques, within the software what we call LMGC, which actually is a software designed to deal with large collection of divided materials, but of course you can deal also with plane contactors. So I shall not go deeply into the non-smooth contact dynamic, because it's not the purpose of my talk. Now, nevertheless, allow me to show you 3 pages of the advertisement for the LMGC software. The first example, as a tribute to Mathieu Renouf, is the example of a 3-dimensional granular material, spheres in a drum, which are used to study segregation phenomena. Another example, as a tribute to Vincent Alcari and his earlier work on monuments made of block, is Pont du Gard, is constructed as an assembly of 35,000 rigid blocks. It's just to give you an idea of what we are doing. And then the third example is related to deformable bodies. It's a study with Yann Monnery, and it shows the way cracks propagate within a fiber-reinforced material according to the properties of the matrix and of the fibers. Now, I consider this dynamical equation, which is not the more general equation. Q is a vector of general variables describing degrees of freedom. For instance, coordinates of the center of gravity of rigid bodies, rotation, or if any deformable body, for instance, nodes coordinates. F are internal forces, P are external forces, and R is a representative of reaction forces, for instance, resulting forces, momentum, or node forces. Of course, we expect shocks, and so the proper space, we shall suppose that, as mentioned already by Jean-Jacques, that the derivative of the variable is bounded, locally bounded variation function, so that R appears as a measure, is a density of reaction forces or impulses if any shock are considered. Now, to describe frictional contact laws, I have to introduce some local variables. Here are 2 contactors with proximal point P, P prime, and the unit normal vector is directed along the P prime P line. Of course, I can define a tangent space, and I introduce the pair of components of the relative velocity of this local frame, tangential and normal. And since Q dot is a bounded, locally bounded variation function, this variable has left and right limits. And also introduce the pair of component of reaction forces or impulses, and the gap G, which is the algebraic distance P prime P. These variables are related to generalized variables at some linear mapping. And one important relation to keep in mind is that alpha is just an index labeling, a superscript labeling some contact, is that the derivative of the gap function is the normal or relative velocity component. To keep that in mind. And so the structures of a frictional mechanical problem is the following. At this stage, we have the space of derivative of the Lagrange variable, representative of reactions, relative velocity at some contact alpha, local reaction, and so you get the relative velocity by some linear mapping, and the representative of reaction force is the image also of local reaction force by some linear mapping, and these two mappings are transposed. Of course, I have a scalar product setting these pair of spaces, these two pair of spaces in duality. And what is the frictional? So the dynamical equation lies at the upper stage. It means that when you give the momentum, you are able through the dynamical equation to get the derivative of the Lagrange variable. And what is the frictional contact relation? It's a relation between the reaction, the relative velocity, and also the gap, which can be obtained through this kinematic relation. Now, this is general view, and this I would like to present some unilateral conditions. The classical form of the non-penetration condition is that at all times the gap should be non-negative. And another equivalent form, which is the viability lemma from just mentioned by Jean-Jacques Moreau, is that if at some time J of the gap is non-positive, then the right normal velocity should be directed upward, should be non-negative. Okay. Jean-Jacques gave enough details about that. So we have to add more physics, and for instance say that we don't consider so far attraction between bodies. They are just repelling each other, which is mentioned saying that the normal reaction is positive. And also, of course, if bodies are not contacting, the normal reaction is still mentioned, but it should vanish. So an alternative form inspired by the viability lemma of Moreau is the following. It appears as a complementarity condition between normal reaction and the right velocity. There is more physics into it. So here you have to assume that if bodies are pressed against each other, it means that its normal reaction force is strictly positive, then the normal velocity, the right normal velocity should vanish. So velocity signorini implies gap signorini, and the converse is almost true if you assume some regularity condition on the normal reaction forces, which are true generally only if you deal with smooth motion. Doesn't matter. Here I mentioned the inelastic shock law, which happens to be equivalent also to velocity signorini condition, assuming some regularity condition. And also, I'd like to mention that Blocher proposes a complementarity condition using the derivative of the normal velocity. So it needs more regularity. I don't write down all the conditions because you have a tree of conditions and it's more complicated, and Professor Blocher is the man to talk about that. Okay, it works very well. I will come back on that later on. So you see that actually you have a choice to model unilateral conditions, where in the simple case where there is no attraction, because the usual simple case. I don't say anything about Coulomb friction. And I like to show what are the consequences of numerical competition of such or such choice. Now, here is again the dynamical equation, and you see, integrate both sides of the dynamical equation on an elementary subinterval ty 1 of length h, step size h. And work so far, there is no approximation. And you see that the mean value impulses emerges as a fundamental unknown. So, if you use numerical schemes higher order numerical schemes, implies that some regularity of the single number are satisfied. If forces are expected, well, there is no means, there is no use getting down other than a first order algorithm. So, except in some cases, why shall I come back later on? So, let's say my first warning is don't try to offer dynamical schemes said to be the most accurate, such as higher order algorithms. I mean more than the first order algorithm. When dealing with when you have to propose discrete form of Signorini-Coulomb relation. Here, this is a proposed form for the gap Signorini. You see that I have chosen as unknown, which is noted an I plus 1, the mean value of the normal reaction force during step ty plus 1. By no means are I mentioned forces at step y plus 1. No, I am just mentioning the mean value of the normal reaction force during step ty plus 1. And here is the gap at step y plus 1. So this is proposed form of the gap signorini condition. You could also propose some form for the velocity signorini conditions. And I say, if contact is not requested, then the normal mean value of the reaction force should be 0. And if some contact is forecasted, then I said that un means the relative velocity at step y plus 1 should be positive. The mean value of the reaction force should be positive, and this product should be 0. So first, you see that this is an implicit way of looking at things, definitely implicit. I am considering gap at step y plus 1. I am considering relative velocity at step y plus 1. And I am also considering mean value of the reaction force during the step ty plus 1. Another comment is that if you compare with the mathematical form written at time t, I consider that the relative velocity at step y plus 1 plays the role of the right velocity. Okay. Now, what is the effect of choosing such or such condition when performing numerical computation? Tu as fait une baguette là, Steve?
Oh, maybe this will work.
Oh, okay, thank you. No, yeah, thank you very much. Yes. So, I'm doing the simple experiment of, let's say, dropping where some particle, some free particle, is arriving with some velocity near a plane of staple. And I plot the gap versus time. In these circumstances, the blue, this is a possible trajectory. That's the blue trajectory. Particle arrives in the neighborhood of the plane, and then at step y plus 1, normal inverses are computed so as to satisfy the gap signorini condition. Means that the gap at step y plus 1 should be 0. Another possible trajectory is a grid one in case some inaccuracy has been produced at some time, and so okay, well, it works also. I shall go with the old-fashioned way, and because some inaccuracy has occurred when the particle has penetrated, and at step 1 plus 1, as prescribed by the gap signorini law, the gap should be 0. Now, you can compute from this simple experiment. I can write down the equation, of course. This is just to illustrate what's happening. The normal velocity is computed like this. It's minus gy, the gap at step y, divided by the time step. So let's consider two situations, quasi-statics and deformable bodies. In this situation, the masses of contacting nodes are negligible with respect to what, well, I make it short. The time step is usually large. So that these impulse are negligible artifact impulses. And the algorithm appears as a gap self-correcting algorithm, since the gap signorini condition prescribes that the gap should be zero. Now, if you are dealing with dynamics of rigid bodies, masses of contacting bodies are not negligible, time step is small, and so these impulses are significant artifact impulses, so that, for instance, if you deal with a large collection of rigid contacting bodies, as I've shown you in the example, the advertising examples, the sample will explode. Now, what's happening if I use velocity signorini? These are two possible trajectories according to the effect of the numerical algorithm. Well, you find that as prescribed by the velocity signorini condition, the normal relative velocity is zero, but the gap at step y plus 1 is precisely the gap at step y. So this velocity signorini condition is fine from the point of view of impulse, but penetration should be controlled. So I propose the following rules. If bodies are deformable and dynamics is not too wide, use gap signorini, else use velocity signorini. So the question, if you know if the dynamics is wide, is up to you. Coming back to the dynamical equation. What is a numerical scheme? A numerical scheme is a way of approximating these integrals. So you have a lot of research to approximate this integral. And well, I shall open the discussion with a method that we are using in the LMGC software, which is called the theta method. Well, it just means that this integral, and if you want to compute the integral of some function f over some interval y, well, you compute an approximate value of f at step y, an approximate value of f at step y plus 1, and you just make some interpolation between these two. This is well known as the theta method. And for instance, if I use this method to approximate this integral, I will find that the Lagrange variable at step y plus 1 is the Lagrange variable at step y plus all right. For my discussion, it's not necessary to come into details. So I would like to discuss now what is happening when you are using such a method. I consider the case of, if you put some Coulomb friction between slides.
Just change the name from slides.
Well, people think that friction is in reason. It's not true. we need Coulomb friction.
This is wild dynamics.
Well, yes, yeah, well, yes. So this is a problem of the collision of two unidimensional elastic bars. You see, they come to each other with equal and opposite velocities, and which is plotted here is velocity of for you the right bar, the end point of the right bar, which is positive. And so you see, before the impact, this velocity this is a numerical example, 5 meters per second. Then during the collision, it stays at 0 during the duration time of collision, and then the bar separates with a -5 velocity, meter per second velocity. So the exact solution is plotted as a dotted black line. Now let's try to analyze shortly this the situation. Okay, and I shall use, because the dynamics is not wide, and because I want to push things on the back side, I like to analyze the effect of the gap Signorini condition. And remember, use the form of this gap Signorini together with this kinematic relation. So discrete form, the standard discrete form, is the following. And then I choose as an approximation of the gap the following formula, you see, which is inspired actually by the theta method approximation. Now, if I use this discrete form, I obtain the following signals, following response. The yellow response is a Newmark method. It doesn't work, but I shall come back to that later. And the theta method, as a matter of fact, we have used here in this experiment, Didier Volat did this experiment, theta equals 0.525. It's an almost conservative algorithm where we have this response. So this is bad. Now, I try what's happening. To simplify the discussion, I assume that I'm lucky and that at step y, where bars are just touching each other, and so it means that the gap is 0. And I have prescribed that the gap at step y plus 1 should be 0. So from this formula, you get that the relative velocity at step y plus 1 is equal to the relative velocity at step y multiplied by -1 minus theta over theta. It means that it acts as a restitution law with restitution coefficient 1 minus theta over theta. So it is the reason why artifact oscillations are generated. Now I try something else, another discrete form, and I decide to compute the gap at step plus 1 minus theta. So in this situation, to compute the gap or to consider the gap at mid-step. Jean-Jacques Monod does that. And this is the new form of my gap Signorini condition. And it happens this time that you have this formula for the gap, for the mid gap. And so the result that you obtain is the red signal. Okay, so you have no more artifact oscillation, and then here I shall not discuss this discrepancy, which is due to other approximations. So here my conclusion is that estimate the gap at the right moment. Estimate the gap at the right moment. And it's true for any method. It's not true only for my favorite method, which is the non-smooth contact method. These things have been observed, or they are recurrently observed by people doing numerical simulations with packs between deformable bodies or rigid bodies. No, I have no time to comment these three other recommendations. To comment, let's say, at all extent. But I say, if the instant of shocks may be carefully computed, so it means that actually you are expecting smooth reaction forces, then you may use higher order algorithms. And then you should use the special procedure to compute the discontinuity of velocity at the time of shock. That's what people are doing when using the newer method. You have a number of tricks, you see, to operate these things. Also, as well, you may use the Blocker complementarity condition. It works very well. We did it in Montpellier, so we can assure it. It works. Now, you see, the question is that you have to compute the instant of shocks. So if you don't have many contactors or too many instant of shocks, so it's perfectly well. And the advantage is that using higher order algorithms, you get better approximation of, let's say, the free flight episodes. All right, but if you are dealing with a lot of contacts, as in the example of the rotating drums, well, you cannot do that. All right. Last comment is, last comment. Then first graph, right relations. And actually, Professor Blocker came into this discussion this morning. Very often you see, I give you the example of plasticity. That's people used to put sigma versus epsilon, and you get, let's say, response like that, experimental response. But if you reverse, then of course you take another graph. So you see, trying to put information on a single graph very often leads to confusion. And as a matter of fact, concerning the question of friction, people are trying, very often you could see that people are trying to put information on the same graph, which is what they call the displacement and also the relative velocity. You never know. You can give all other kind of example. You see, for instance, with cohesion and things like that. So right relation, don't trust graph. And last comment is that uniqueness is not the rule in rigid bodies collection. And the algorithm operates its own choice. And there is still some mystery about the way it does it. But fortunately, when dealing with large collection of rigid bodies, the results are statistically relevant. Okay, thank you very much.
Michel Jean. Yes.
So I wonder if you can elaborate on the third from the bottom bullet. The instance of shock may be carefully computed. You said higher order algorithms are used. What kinds of higher order algorithms?
Oh, but for instance, a numeric method.
So you're talking about the numerical method itself?
Yes, the numeric method itself is
not,
higher order.
Not first order, but second or third.
Yes, you have to use tricks and it works very well. Okay. And actually, the trick is that you know precisely the instant of shock. There are several tricks about that. And it works. So I am not against higher order approximation, but you have to be careful about that.
Okay, and yes.
The last item that you have on your list, you said uniqueness is not the rule in rigid bodies.
Yes.
The source of the non-uniqueness. Yes.
All right, there's some transparency. It's an elementary example. Okay. Well, it is a it is a simple example of a rigid disc wedged into between two plates with dry friction. All right, and so you see that and submitted to gravity force. So in this to be equilibrated, you see three forces should meet at a common point: the gravity forces and the reaction forces from contacting points A and B. This contacting force should lie in Coulomb's cone, which are here colored in yellow. So an elementary analysis shows you that any point P lying in the red segment Ij is a candidate to be a meeting point for forces equilibrating the disc.
Okay, but this actually would suggest that the situation is not modeled completely in any way.
It's not.
It's not modeled completely.
Well, this is the fact with rigid bodies. These are modeled with incomplete information. No?
Yeah, the computer I can show you can call this. Yeah, the computer
Okay.
And there are some other examples of that. Any more questions before we move on? Okay. Well, perhaps we should move on then. I know I'd like to ask some questions myself later on. But we're going to move on. We have 2 half-hour talks, and the first will be, let's see, from Jeff Trent.